Good afternoon, students. So we will be talking about the statistical process control. Before we really go through the details of this particular discussion, there are certain prerequisites which are required for this discussion, and I am assuming that you are aware of the project management processes such as the process estimation, planning, project plan, then schedule, effort, cost, and quality. I am also assuming that you are aware of the quality control processes like the reviews and testing, where in the reviews you capture the errors and in the testing you capture the defects. Then this particular statistical process technique will be used for monitoring and control. So I am assuming that you have already studied the project monitoring and control part of the project monitoring, where you are aware of what are the different measurements to be done, as well as the different data to be collected during the measurement, and some exposure to statistical methods and techniques is assumed, like what is the mean, average, what is the standard deviation, and things like that. So if you really see the statistical process control, it helps you to monitor and control the schedule, effort, as well as the quality. Efforts is equivalent to the cost using the statistical methods. Let's say what is the statistical process control. So statistical process control uses the statistical methods for the quality control. SPC, that is statistical process control, is applied to monitor and control the processes. It ensures that process operates at its full potential. The main tool which is used for the statistical process control is called control chart. The control charts are originally developed by Walter Shewhart in early 1920s, and they are prepared based on the historical data. And the control chart really specifies the process capability of your organization. If you really see control chart has got various characteristics. First of all, it is a graph. It is prepared as per the time on the x-axis, or it can be different instances of the samples on the x-axis depending on the control chart, and on y-axis you either plot the average as well as the upper limit control and the local limit control. The local limit and upper limit controls are calculated based on which process control chart you are using, and normally the UCL and LCL limits, they are plus minus 3 sigma from the average or the mean. There are different types of control charts. There are two main types. One is the control chart for variables, and other one is the control chart for attribute. Control chart for variable is further divided into two different types. One is the X bar chart, which uses the average of the sample or the mean of the samples, and the second one is the R chart, which uses the range of the sample, that is the variability of the different samples. The second main type is the chart for the attributes. Again, chart for attributes is divided into two different parts, the P chart and the C chart. The P chart uses the randomly selected portion of the sample, while the C chart uses the number of defects in a sample. So that is the difference between the P chart and the C chart. We would now understand how the charts are prepared. So in the today's discussion, I would only take you through the X bar chart, the complete example, including the formulas. Using the similar formulas, we can prepare the other charts as well. So if we really see the X bar chart, I have collected total 10 samples, and the samples are about the slip ring diameter. So it is a manufacturing process, and and you are calculating the or measuring the slip ring diameter in the process based on the capability of your manufacturing process. This need not be the manufacturing process. Similarly, you can have let's say the schedule in your project. The samples will be the number of projects. So let's say you can have 10 different projects, and observation will be the schedule in each of the modules. So you can consider total 5 number of modules and the schedule for each of those modules. So not necessarily it can be a ring, it can be even software projects or any of the APC or any project manufacturing project. So if you see here the samples, we have total 10 samples and the 5 instances of each samples. From the 5 instances, we have added all the 5 samples in the first row and calculated the addition and then divided it by 5, because there are 5 samples, and you get the mean value of those first sample. Like that, for all the 10 samples, we have calculated the average, that is the x value. Then we have taken the total of the x value, which is 50.09, and that is divided by the number of samples, which is 10. So if you see the mean average, that is x bar, it comes to 50.09 divided by 10, which is approximated to 5.01. So this is actually the x value, which represents the mean value in your control chart. Then to calculate the upper control limit and the lower control limit, the standard deviation is used, and Z is typically 3 sigma, or the 3 is the value of the Z. So if you see here, the UCL will be the x bar, which is 5.01 plus 3, and the mean of the sigma x. So mean of the sigma x is calculated based on the standard deviation divided by the number of samples, which is 10. So 0.08 divided by root 10 multiplied by 3 plus 5.01 is equal to 5.09. That gives you the upper control limit. Similarly, 5.01 minus 3 into 0.08 divided by root 10, it gives you the lower control limit, which is 4.93. So using this x bar and the UCL and LCL, we calculate the bar chart. I have plotted here the bar chart. So as you see on the x-axis there are sample numbers, and on y-axis we have the x bar mean, and each of these 20 points are calculated, and you get the graph where we now see for every sample how your data shows whether so you have to be, as long as the data is closer to your mean value, really your process is quite stable, but wherever the data is touching, for example in this particular case there are 2 data points where the data is almost touching your UCL and LCL, so we need to worry about those instances, and you need to go into the details. For example, here here if you see the slip ring manufacturing, you will have to see whether the problem was with the machine, we will have to see whether the problem was with the tool which was used in the machine, or it was based on the operator. So we need to do 5-why analysis and do the root cause analysis, and accordingly find out the root cause and take the corrective action in your project. Similarly, if it is used for the project control in terms of schedule, then wherever project deviates from the average line, then you need to again go into the root cause analysis and do the 5-why analysis and see what are the different reasons, and take the corrective action before it is too late in your project schedule. So thus we can use the different statistical controls and monitor the different types of charts. Now these charts can be used for monitoring and control of the project. Different historical data are used to plot the mean value, lower and upper control limits. Now this particular historical data of an organization really depicts defines your process capability. So it could be the capability of your in terms of your schedule, capability in terms of your efforts or the cost, and the capability in terms of your quality, that is the defect analysis. Once you have the capability of the organization defined, normally in the organization you will have the quality team which will calculate the organizational capability and depict the different types of control charts.